Hi guys, Dr. B here. This is topic 6.4, heat capacity and calorimetry. The objective is to calculate the heat absorbed or released by a system undergoing heating or cooling, and we're going to use that based off a couple of things. Based off the mass of the water or the amount of the substance, the heat capacity, and the change in temperature. So the quantity of heat, or Q, is a measure of the transfer of energy, of thermal energy between two bodies, one that needs to be higher in temperature and the other is going to be cooler. Three factors contribute: the mass of the object, the specific heat capacity, and the change in temp, which is final temperature minus initial temperature. Specific heat capacity, what is that? It's the amount of energy that is needed to raise a temperature of 1 gram of a substance by 1 degree Celsius. So let's say we use water, for example, as a higher specific heat capacity compared to other substances, 4.18 joules per gram degree Celsius, while metals are lower. The label is C, and the unit is joules per gram times Celsius or Kelvin, depending on what they give you or what's given. The heat is a form of energy that flows between samples of matter because of the difference in temperature. Label is Q, and the unit is joules or calories. So important unit conversions to look at. So 4.184 joules equals 1 calorie. 1,000 small calories is 1 big calorie, or big cal, or 1 kilocal, which is a small calorie. 1,000 joules is 1 kilojoule. This should be familiar for you if you did physics. You can calculate heat when there's a temperature change using the formula Q equals MCAT, or Q equals MC delta T. Q is heat, M is mass, C is specific heat capacity, and delta T is change in temperature. There's no actual A, but the delta looks like an A apparently. So a calorimeter measures the amount of heat transferred during a reaction. We're going to try to do this in the lab with a styrofoam cup and all that. Hopefully it works out. So calorimetry is the measure of quantity of heat exchanged. If the energy from an exothermic reaction is absorbed in a container of water, the change in temperature of the water provides a measure of the amount of heat that was added. So let's look briefly at the first law of thermodynamics. In an isolated system, heat cannot be lost or gained, it can only be transferred. So a typical experiment can be used to find the specific heat of an unknown by heating the metal to a known temperature and then placing the metal in a calorimeter containing water. So essentially, the heat that is transferred from the metal to the colder water will then, when they will reach thermal equilibrium, then you can find out how much heat was gained by the water to find the heat lost by the metal. So what do I mean by that? The heat of the metal will equal the heat of the water, but the opposite sign. Since we know that Q equals MCAT, we can have this equal to each other. The mass of the metal times the specific heat of the metal times the change in temperature of the metal will equal the opposite of the mass of the water times the specific heat capacity and the change in temperature of the water. Each substance has its own specific heat capacity. Look at aluminum and lead. There and there. You'll notice that if the amount of energy is the same, the mass is the same, and the change in temperature is going to be different. So the higher the specific heat is, the change in temperature is lower. So you need more of it, like a higher temperature, higher energy, for it to actually increase in temperature. Okay? Specific heat capacity is a measure of the amount of energy needed to raise 1 gram of a substance. You can look at the molar heat capacity. It can be given to you. It's the amount needed to raise 1 mole of a substance by 1 degree. You may be given both, but you may need to use some dimensional analysis to get the units to the correct one. Chemical systems change their energy through 3 main processes: heating and cooling, phase transitions, and chemical reactions. So we can see that by using QMCAT, we can see that by having a temperature change occurring, you're changing the kinetic energy of the particles. Next lesson, 6.5, we're going to look at when a phase transition takes place, how to calculate the heat of that. But for now, we'll focus mainly on just a calorimeter and heat temperature changes by heating and cooling. Almonds and cashews were burned in a bomb calorimeter containing water. The following data is collected. You have almonds and cashews different mass of water for some reason. The specific heat of water is the same. Initial temperatures are the same. Final temperatures are different for both. The mass of the nut that was burned, 6 grams and 5 grams for almonds and cashews. So the question is, calculate the heat gained by the water for each nut. So for almonds, you're just going to use your QMCAT. So because we're using water, the density of water is 1 gram per 1 mole. So that means that grams and moles are equal to each other for water. So for almond, so we're going to use Q equals MC delta T. Q equals the mass of the water, so 2,000 grams times, they give us a specific heat of 4.18 joules, grams over grams times degrees Celsius. Change in temperature, so 40.5 divided by 22.5 degrees Celsius. So I'm using that specifically so you can see what I'm going to get. So 40.5 minus 22.5, this is 18.0, sig fig rules keeping in mind. So 2,000 times 4.18 times 18.0, it's going to give me 150,480 joules, or about 150 decimal kilojoules. For cashews, Q equals 1,000 times 4.18 joules times the change in temp, 51.3 minus 22.5. So I'm just going to do the math for this. So 1,000 times 4.18 times 51.3 minus 22.5. So I end up with 120,384 joules, or approximately 120 kilojoules. Calculate the energy for each nut, and calculate the energy for each nut, which provides more energy per gram. So almonds, we're going to use an equation. It's going to be delta H equals Q over M. So 150 kilojoules, which is from the problem, divided by the mass of the nut, which is going to be 250.0 kilojoules per gram. For cashews, same equation. So it's going to be 120.0 kilojoules, 120 point, divided by 5.00 grams, which equals 24.0 kilojoules per gram. Almonds provide more energy per gram, 25 versus 24 kilojoules per gram. So almonds get more energy per nut. 50 mLs of 0.500 molar HCl was added to 50 mLs of 0.500 molar NaOH. The initial temp is 19.8 degrees Celsius, reaction occurred below. Final temp is this. Calculate the heat gained by the mixture. So the total mixture is just going to be my milliliters added, and because it's aqueous, we're going to assume it's water, and the density of 1 gram equals 1 milliliter, so we can use the mass of the water. So Q equals MCAT is my equation I'm going to use. Q equals 100.0 grams times 4.184 joules per gram times degrees Celsius times 26.3 minus 19.8 degrees Celsius. So their sig figs are going to be 3 sig figs, so 26.3 minus 19.8. This, based on that, gives me 6.5 degrees Celsius. So it's got to be 2 sig figs. I apologize. So 100 times 4.184 times 6.5 gives me 2719.6, which is going to be 2,700 joules. What is the heat of reaction per mole of NaOH? Well, we can see from the question stem, the initial temperature increases to 26.3. That means that the actual mixture, so the water, if you will, the surroundings, the temperature increased, so the actual reaction that occurred released energy. So this was an exothermic reaction. So the heat of reaction per mole of NaOH, so that would be Q, I guess NaOH if you want. This will equal the energy of the whole reaction, but because it's exothermic, the heat of reaction to NaOH to the products means it's negative because it releases energy, so negative 2,700 joules divided by 50 mLs of NaOH. So I'm going to convert this to liters with my, kind of want to get rid of that. For my, get my liters, so it's going to be hold on, I'm trying to think. 1 liter on top, there you go. 1,000 milliliters on the bottom. Then you're going to take your 0.500 molar NaOH, so 0.500 moles over liters of NaOH. You do your math, you will end up with negative 110,000, is that right? 110,000 joules per mole. And then in the end, it's negative 110 kilojoules per mole of NaOH. All right, so if you have any questions, please let me know. Thanks, guys.